After learning the basics of the Bernoulli's equation, now we are in a position to solve any differential equation in this certain form with the help of this method. So now we are going to do an economic application, that is the average cost function will be analyzed using the Bernoulli's equation. So as we know that average cost is represented with AC and the output is what determines the level of AC, that is average cost depends upon output in simple approach. So these are the dependent and independent variables. Now this equation is given, we are given that the derivative of average cost and then adding the average cost with its ratio with Q, we get the cube of average cost. So it's an elaborated equation. We are writing it in such a way that it makes it clear for us to understand that this is AC and this is also the AC. So AC is basically behaving like Y here. The variable, the dependent variable is right now AC. So this is now comparable with the Bernoulli's equation. We can easily compare it because we can see this 3 here as the power. So let us compare it with 3, this the standard form of Bernoulli's equation. As we compare, we get that in place of Y we have AC, we have R instead of 1 over Q, we have instead of R we have 1 over Q, instead of T we have 1, and instead of M we have 3. So we can extract these values because these are the values that we can use in order to find out the solution of this Bernoulli equation type of function. As you can see, it is now confirmed that it is a Bernoulli equation type because it is adjacent to the standard form. So you remember that we assumed z is equal to y1 raised to the power 1 minus m. So we can remember this, instead of y we have AC, therefore we have AC here, and instead of m we have 3 here. So z is equal to AC raised to the power 1 minus 3 will be AC is equal to minus raised to the power minus 2. So we can use this for substitution and the remaining solution. The linearized form of Bernoulli's equation is this, as we have already proved in the lecture where we understood the basics of Bernoulli's equation. And here we can put the values, which is easy for you. You know that the value of m, the value of r, and the value of t are to be substituted, which are already brought out by using this comparison here of the standard form and the given equation. So this is simple algebra that you can easily handle, and after it we are going to convert it into the first order differential equation form, in which we have derivative. So we have to divide with dq throughout, and when we do, it becomes dz over dq. So throughout, when we divided, dq appeared in all of the places, and this would reduce to 0, whereas this will be cancelled out, leaving 2, and this will be minus 2 into 1 over q z, and simplification got rid of these dq's, and this dq will remain here. So this is now going to be adjacent to the first order differential equation. Let us see. This can be treated as the derivative term, this can be treated as the dependent variable, and this can be treated as the term on the right hand side, which is either a constant or a variable. Here it is a constant, that is, it is equal to 2. So this is the coefficient term, and in this case it is a variable term because there is q in it. So when we have q, it means that it is a variable, and the coefficient is a variable coefficient. Let us write this variable coefficient. and you can see that we are highlighting that they are equivalents. Here it is usually WT. So since the independent variable is not T, it is basically Q, so we are writing WQ. And in the same way, here instead of T we have Q as the independent variable. Here again T is not there, rather Q is there, which is the independent variable in this specific economic application. So these values are noted here. Instead of Y we have Z, and instead of T we have Q, and the value of UT is actually the value of UQ, and it is equal to this in terms of Q, and the value of WT is in terms of Q, where the value is equal to a constant. So we have a case which is actually the first order differential equation with variable coefficient, but a constant term. In this case we have a constant term. So it is suitable to use this formula because it has the ability to incorporate the variable coefficient. So this is a usual procedure that we have done before in the introduction of the Bernoulli's equation. So we are going to put the suitable variables here. Instead of Y we have AC, instead of T we have Q, and therefore dt is replaced with dq, and this term is replaced with terms containing with q and not the t. So the formula will look like this, and we will put the values. The first thing that we would like to do here is dz over dq. This is the standard form comparing it, and we are going to extract the value of uq here, which we will put here as well as here. And since we are to take the integral, so it's better to do it in a clean way and integrate it separately and then see that what is the answer. You can do this integration by yourself, it's easy to do. The only important thing to note is that we are dropping the constant of integration to keep the things easy. After doing this simple integration, you will get the answer of integral of uq, which you can put back into the formula so that we get to the solution. So the formula has accepted the values. Here the integral of uq is substituted, so is here, and here w is substituted. So the solution is there afterwards, and I hope you can easily handle it. This is where we apply the law of logarithm, where the coefficient comes in the power of the variable, the log of which is being taken, and here again the coefficient comes into the power of the variable, the log of which is being taken. So the good thing is that we can cancel out the exponent and natural log. It is done here, and we are left with q square only due to this, and q raised to the power minus 2 only. So we can rearrange it, and we have done the integration while omitting the constant of integration to keep the things manageable. So the constant of integration is omitted, and the integration, the result of it is here. And now we have the the simple algebraic simplification that we are doing here. This q square is being multiplied in various places, and you can see that it is allowing us to simplify. This will reduce to q raised to the power 1, and this q square will remain q square, and finally we will get this answer. So you can pause the video and verify these calculations, simple algebraic calculations. Once we have this, we can revert back to y, because revert back to AC in this case. Actually in the formula we have y, but in this case we have AC. So we in the beginning assume that z is equal to AC raised to the power 1 minus m, which is 1 minus 3, which makes it minus 2 in the power. So we are putting it back in place of z, and then this is the form This minus 2 when reciprocalized is brought to the other side and it gets reciprocalized. So this is the situation. We can reciprocalize it further to change its sign, that is turn it into a positive sign, so it becomes 1 over 2 as the power, and we know that this average cost is dependent upon q, so we have written this q in the functional form here. So we can also write it in this form. There will be no harm if we write it like this. However, in our solution we have written it, you know, with power of 1 over 2. So this will be the solution of the this is the given differential equation, and this will be the solution by using the Bernoulli's equation. However, its diagrammatical depiction can help us to better understand the phenomenon, which is the economic phenomenon in this case. Now, if I plot these, you know, two variables, that is q and then AC, which is dependent on this, by putting various values of q, I can make a table in this way by experimenting with 0, 1, 2, and 3, and so on. So I can get with different values of AC that I can plot here. If I do so, the diagram will look like this. So you can see it's clearly a downward sloping curve, and it is becoming a kind of asymptote. It is not merging with the marginal cost, it is just getting close to it. And we remember that the average fixed cost also has this shape usually, and when it spans to such a long interval, it means that the average cost, the fixed costs were very high. When the fixed costs are very high, we are dealing with a situation which is known as natural monopoly, because in the beginning of the natural monopoly, the fixed cost is very high. So when we divide this value, and you know, with q, and the value of q is increasing, the ratio declines. That is the ratio which is the ratio of fixed cost and output. So when we make this diagram, it will be a value which will decline gradually and will, you know, come down gradually in a very slow manner as it spans further into higher values of output. So this shows, this higher level shows that we are dealing with a kind of natural monopoly, because the fixed cost is very high, and the average fixed cost accordingly will have this downward sloping trend. This actually is not just a downward sloping trend, it is basically known as the rectangular hyperbola. And it is holding here, this is a kind of shape which is rectangular hyperbolic in nature. So by plotting this solution that we got, we get to know that this is a relationship of average cost with output, and it is showing where there is a possibility of having a natural monopoly. And in this way we have applied the tool of Bernoulli's equation, and that has enabled us to develop the average cost curve of the given equation, and it also helps us to understand the nature of the firm that we are dealing with. Thank you.